To go over the concept of derivatives, let's go over an analogy. Let's say you were driving a car and we graphed a relation between how long it's been and the distance you've traveled. So at any point in time, we can see that when you have traveled, say, 30 seconds, we see that you have driven 200 meters. So how is this related to derivatives? I'll explain what derivatives are and show you how they relate. Derivatives is the instantaneous rate of change at a certain point, that being a simple definition of it. So what does this mean? If we go back to our driving example, the instantaneous rate of change at this point is going to be the slope. So if we consider what this would be in real life, this would be the velocity of the car. So if you're looking at your speedometer at this point, that's your speed. That's what the derivative of the graph is, or at least the magnitude of it. We learned at the beginning of high school that the slope of a line is given by the equation y2 minus y1 divided by x2 minus x1, or basically saying the slope of a line connecting 2 points. This gives you the rate of change or the slope of a line. But what if we extend this idea towards a curve or a nonlinear graph? Then we don't know what the slope is of the graph. Here it seems that the slope is very small, almost zero, and here it looks almost vertical, so the slope is really big. At any point, the slope or rate of change changes and is different from anything around it. Going back to the car, if you were looking at your speedometer here, it might say 79 kilometers per hour. Here, it might say 81 kilometers per hour. But if we want to find what the derivative or rate of change at the point in the middle is, we can't use any of these other numbers since the rate of change at that point is going to be different from the ones around it. However, they're still useful because they're so close to that point, we have a general idea of what it might be, and we could make an educated guess that it's going to be roughly 80 kilometers per hour or somewhere in that ballpark. But of course, we want to get infinitely precise. We want to find the exact rate of change at that point, and how does infinity, like the idea of limits, play into this as well? Let's look at the graph of f of x is equal to 2 raised to the power of x. Here we have the graph and it's increasing, and let's say we want to find the rate of change at this exact point right here at x is equal to 1. Now, how can we use the idea of limits and becoming infinitely precise to help us here? Let's connect these 2 points right here. If we connect them and find the slope of this line, we can have a general idea of what x equals 1 and the derivative of that point will be. However, it's not a very good estimation. So let's shrink the distance between those 2 points and closer together as they come even closer to x is equal to 1. Closer, closer, and now closer. So here we have a very good idea of what the slope at x equals 1 is going to be. But we want an actual number. We want to get infinitely accurate and precise. So you can see what I'm going to do. We're going to keep closing the gap closer and closer until we are infinitely close to the point. Now zooming in, we can see that the line appears to almost touch the graph at exactly x equals 1. And this is what we call a tangent line, and this is what the derivative of that point is if we were to take the slope of this line. If you're curious, the slope of this line is 2 times the natural log of 2. However, calculating derivatives isn't as tedious as this, and there are many methods to find the exact slope of each point.